So yes, this week we are going to go through the Big LLM Architecture Comparison from Sebastian Raschka, which we're just going to kind of walk through the various architectures as he kind of goes along them, and then see if there's any interesting sort of discussion points along the way. And we brought Trusty GPT with the paper in his context in case we have extra questions. So. Um, yeah, I guess. Do we? What do we think? Should we just? Am I reading aloud here, or what are we? What's the plan? I
I don't
don't
know that you have
mind
to
if I
read the
do.
intro. We could just jump to the first model, which is DeepSeek, and then look at
Sure.
the highlights of the different features, right? So he's got MLA as the first highlighted architectural
Yeah,
design.
makes sense to me. Let's see. So, Emma, yeah, true enough. Okay, three R1. In case you're not familiar, R1 is or DeepSeek is the whale company. They do open source models, and it was kind of a big deal when they dropped R1 especially and kind of V3. V3's architecture I've heard is like fairly interesting and was like pretty was top dog for at least a little while. And then R1. So let us have a look at what kind of developments we have. So we have MLA, which was multi-headed latent attention. Um,
Hey, Warren.
we have some background on why
Uh,
it's used, which, as I recall, was footprint. Yeah,
I just was getting a request to kind of zoom in a little bigger font.
zoom in a little. Okay.
Yeah, and if
Let's
we
see.
don't need that side window of ChatGPT's help,
Yeah,
maybe
we
we
could
can
do
just
that. Yeah,
make it all
we could
full
drop
screen
that.
for now. Then we can zoom in maybe a little more.
Yeah, I don't know. I think at this point we're height constrained, not width constrained.
Do we still have Warren?
If we do this, and then we do that, we can control plus, or is it plus? So we got, okay, sorry.
Thank you.
Okay, let's see here. Sorry, my machine is not cooperating at the moment. Um, okay, is this good? Does this work?
Yes, this is good. Thank you.
Okay, cool. Got it. Okay, so we've got uh we have GQA, which is the standard replacement for MHA in recent years. And so we have MLA in this architecture. So MHA is each head is going to have its own set of keys and values, and then GQA is going to have the grouped heads share the same keys and values, which is obviously a little easier on your GPU. And then we have let's see.
So MHA is kind of the standard attention when we talk about attention.
Right.
Attention is all you need type of thing.
Yeah, yeah. I think, yeah, we mentioned that. Core idea behind GQA is to reduce the number of key and value heads by sharing them across multiple query heads, which is just a description of this thing right here. So this is like, okay, let's save a little space.
And Ted, do you recall what there was one where it was essentially a group of one? They were all shared, weren't they? Am I
Yeah,
remembering
yeah,
correctly?
it didn't work very well, but there's, what did they call it? Um, I can't remember, but
Okay.
basically, so if you have 16 heads, the original paper says you would have 16 queries and 16 keys and 16 values. And then what we haven't talked about is that um, when you're doing things, you'll just use the query once and then you kind of throw it away. So you don't really care how many of them you have. You don't care as much how big they are. But those keys and values you're going to use for every token further on in the sequence, you
Long
know.
history. Yep.
And so if you have a very long generation, now we have long context, right? Hundreds of thousands, then you could be using these hundreds of thousands of times. And so then that gets expensive and it grows the size of your KV cache. So the original idea was each token position has their own unique queries and keys and whatnot. But within one given token position, if you're using 16-way attention, maybe you can get away with one key and have 16 different queries, but they can just kind of, if you're I'm just going to make the math really easy. So if your hidden dimension is 16,000, which is a little too big to be realistic, but if it's 16,000, you have 16-way attention, your key is still dimension 1,000. So maybe the queries could just match up on different subsets of that 1,000. Maybe it's good enough, but it turned out it hurt performance. So grouped is usually, my understanding, is only a factor of 2. So if you have 16 queries, you have 8 keys. You don't reduce it that much. It's just a factor of 2. But that does cut in half, fully in half, the size of your KV cache.
Oh yeah, I was just trying to think. I had thought of something, but that was a quantization thing and not necessarily an attention thing. So I was thinking of the wrong thing. GPT came up with just a few other kind of sort of descriptions of other types of attentions, which are kind of interesting here. I think it appears that they kind of build on the principle here. So we with this one, which is multi-headed latent attention. So rather than compressing to let's just have let's have some portion of the heads try to share their resources as they're going through these keys and values. Let's try and compress the key and value tensors into a lower dimensional space before storing them in the KV cache. So we do compression prior to putting them in the cache to be attended to, if I'm understanding that correctly. And then at inference time, the compressed tensors are projected back to their original size before being used, as shown in figure 3 below here. This adds an extra matrix multiplication, but reduces memory usage. How does that work?
Yeah, so I don't know about. I feel very scared saying this, but I'm pretty sure Sebastian Raschka is wrong here. So it conceptually adds an extra matrix multiplication to project it back to full size. Okay. In fact, what they do is they fuse that extra matrix multiplication with the next matrix multiply, and so there is no actual explicit overhead for the latent. I'm not going to say for the MLA. Okay.
So
There ends up being a little bit of extra overhead for how they do the rope embeddings, but the actual latent thing using a smaller one, there's no extra. There's matrix multiply in the naive implementation, but in the actual implementation, there's no extra step.
what's the multiply they fuse then? The reprojection and the query?
I think it's when they dot the keys with the query.
Okay.
So you don't say short query, matrix multiply, then matrix multiply it with the query in order to get your attention scores.
Short key.
You just fuse those two together.
It'd be the short key reprojected then times the query, right?
Mm-hmm.
Because the keys are the ones that are compressed into latent space. Queries aren't, are they?
But there's a detail that I've never really understood, and you see the bottom of Warren's screen. It says, as a side note, the queries are also compressed, but only during training.
Oh, okay.
So I've never fully understood that part.
Okay.
But you have a hand raised, Warren. So I'll go to Dave in just a second. But so the key idea here is this and grouped query are all about saving memory in the KV cache. It's not about less compute, less whatever. It's really about a less GPU memory. And so one thing you can do is you can cut down on the number of your keys. The other thing you can do is you can cut down on the size of your keys. And that's what latent attention does, is size instead of number.
So do they pay? So in terms, so that would let you fit more model into GPU cache, but I presume that there's some kind of trade-off there in terms of like actual flops being applied to the operation kind of thing. It's kind of where I'm.
So yeah, actually, depending on how you implement it, I'm not sure how you implement grouped query. If what you do is you just sort of, for two-way, if you just duplicate all.
He unmuted very quickly, so that must be automated.
I'm not sure exactly how it's implemented, but if you naively just have half as many keys, but then you make a copy of each one, and then you do the matrix multiply with the queries, then you're not really saving on any flops. So, but I'm not sure the exact code that they use to do it, to answer your question.
Got it. Let's see. Okay, so these at inference time, these compressed tensors are then projected back to their original size before being used. So an extra quote unquote extra matrix multiplication during inference time, but then reduces memory usage, which I think makes sense to me. If it's the way that we're going to do our training, we want it to fit on a smaller GPU, and we're willing to pay that cost back a little bit during inference time is kind of what it sounds like. Then that makes sense to me. Let's see. MLA is not new in DeepSeek v3, as its DeepSeek v2 predecessor also used and even introduced it. And then interesting ablation studies that may explain why they chose MLA over GQA. So let's see here. Unlike what previous papers found, this paper finds that MHA performs much better than GQA. Much? Okay, like 4 or 5 points. That's something. That's significant. And then we have memory requirements for MLA are much lower than for MHA, which is definitely tracks. And then MLA performs better than MHA, here tested on mixture of experts architectures. MLA, large MOE with MHA versus MLA. Okay.
So when you use half as many keys, you take a performance hit on perplexity and on benchmarks. What DeepSeek found actually was when they compressed them, not only do they not take a hit, but somehow they actually got a slight increase on their benchmarks.
Interesting.
So I haven't seen research that really tried to replicate that and understand, is it actually an increase, or is it just, a little bit of, when you randomly, right, little random noise, and they happen to score a little higher.
Yeah, I guess that.
Are those, noticeable improvement though, isn't it?
It looks like it to me. Like
I don't remember it being this high in the actual paper, so I'm not quite sure, but.
Let's see. As shown in Figure 4, GQA appears to perform worse than MHA, whereas MLA offers better modeling performance than MHA, which is why they likely chose it. It would have been interesting to see the KV cache per token savings comparison between MLA and GQA as well. That would be interesting.
Yeah, so I could, come up with some hypotheses. They ended up changing the way rope works in order to accommodate this compression. And I've been thinking, like, it's kind of dumb to apply rope to every single dimension of your vector if all we really care about is the low frequency ones and some just high level info about, hey, this token's really far away, long time ago. But you really only care about this token was one token ago, two, three, approximately that number. And then once you get to many, it doesn't really matter. I have trouble believing that any model is calculating the token that was exactly 17, let alone 145 before me.
Yeah.
And especially when you consider that tokens don't equal words, there could be text that actually says like let's say you had a certain poem that had a word count per line, whatever. This still wouldn't be useful because some words are multi-tokens, and you would need a completely different mechanism for counting words. So it might be because they ended up not rotating their queries and keys themselves, but rather adding a little bit of dimension for the rope.
Right. So if I recall, they added the position information that concatenated it on, right? During,
Yeah,
yeah, they didn't store it with it in there. So
right. So
another way
so
to think about
normally
it,
if your queries and keys are 1,000, you rotate both of those thousands, and
right,
then you end up getting the net difference when they multiply. But what they did is they say, oh, we'll just increase it from 1,000 to whatever 1,200, and all the rope is in that extra little
right,
bit.
right. Which another way to think about it might be that by not embedding the rope into the KV cache, it gave you a little bit more expressivity in the
Right, you're
KV
not
cache because
stomping on your queries and
right,
keys.
right. You don't have to store the position. It's external kind of
Yeah.
positional. Do you know, Ted, do you have any update, any sense of when we read through the MLA, it sounded good, performance looks good. Um, has it caught on? Have you heard of other models, more recent models
I
using it?
Not much. I think maybe there was one model that tried using MLA. So I don't know if it's a matter of time. It takes you a little while to because like you have a code base, right?
Yeah,
You're the
yeah,
Llama team, and you take your
right,
Llama 3 code and use it for 3.1, then use it for 3.2. So at some point you'll have to like, ugh, I'm gonna actually like bring in new code.
right, right.
But
Let's see.
Dave, did you still have a
So
question? Sorry, you've been very patient.
yeah, so there's two questions. So uh, I I mean I get why GQA performance will go down, but implicitly MLA performance going up was not very clear. But then I guess you attribute this to the rope changes. Otherwise, I mean, there's no reason if you have the same dimensions and everything same, except that you're saving memory for KV cache. There's no reason why the performance. I mean, no. Uh, eh, I mean, unless it can be explained mathematically, that latent somehow has more expressivity than non-latent. There was no reason to see performance gain. But I guess what you explained already is important, right? In terms of the rope changes.
As far as I can think of, they're using just a matrix multiply to compress it. So they're not using fancy compression. They're just right.
Yeah.
So if you have multiplied by 1,000 by 256 matrix, then it shrinks from 1,000 to 256. And then they do the reverse to go from 256 back to 1,000. So I don't think you get any increased. Um,
Expressivity.
yeah, yeah.
Yeah.
Unless somehow
Could
the
you get,
rounding of it actually helped, which I wouldn't think.
No, I don't think so either. And
could,
the can I just make, sorry, just one point very quickly, that definitely, when we are doing inference or during training, if we also have the same QKV appearing, then we will see uh, huge memory gains because the KV cache, depending on the latent, which is substantially smaller than the actual dimensions of the original K and V, we will end up saving a lot of memory in the inference engine because these days, KV cache is implicit, and in any of the inference engines, VLLM or LM cache or SL, SGLang or any of those, and with you can also specify the uh, with this approach, you will end up saving a lot, is what I'm thinking. And memory
Yeah.
savings are there, but during execution time, you anyway have to invert it back to the original memory. So it saves the GPU memory, but not the execution flops, or in fact, it increases.
Cool.
Yeah, when I threw GPT at it, or what made sense to me was the kind of point here of like if you're directly compressing the full KV and you're doing like a rope baked in, but only of the important parts, then you're forcing that compression process to preserve some kind of like extra structure that it wouldn't normally have to. So that's kind of like where my hunch is of like during the compression, then perhaps the compression decompression kind of thing that you have to do. It could be that the presuming the compression is like not lossless, then it could be that actually like going through the compression decompression step could like provide that advantage because of the kind of like baked in fuzzy rope kind of thing that you're doing there is kind of where my head is heading with that, but also from ChatGPT, so kind of a tough could go either way, I suppose. Let's see. So clever trick to reduce KV cache memory, slightly outperforming MHA. Good stuff. Mixture of experts. I'm pretty sure we all know what a mixture of experts is. Let's see. It didn't invent it. Quick recap, sure. Replace the feed forward module with multiple expert layers, where each of those expert layers is also a feed forward module. We swap a single feed forward block for multiple feed forward blocks, as illustrated in Figure 5, which is a very good figure. I might save that for later, actually.
I had a question about this one.
Hmm.
If we look in the feed forward smaller block, there is the circle X, which I assume is element Y's multiply. Is that right? Is that how you implement the router essentially?
No, no, no. This is the llama style MLP. So the original Vaswani transformer, you just had two linear layers.
Yeah.
And so this is the gated linear unit that llama introduced. And all of these models use this instead of the old-fashioned original Vaswani MLP.
Oh, okay. And so the difference is just that there's in the middle of it, there's a gating that is also learned. That other linear layer bubble
Yeah.
is another learned thing.
Yeah. So you have a little bit more expressivity. I think you have a little bit more cost if you sized everything the same as a Vaswani MLP,
Okay.
right? So if you went from 1,000 to 4,000 with a factor of 4 as the hidden dimension,
Uh-huh.
right? Here you'd have two of those 1 to 4,000s, but
Right, right.
only a single 4,000 to 1,
So it's kind of a 50% parameter increase relative to the original.
and some extra matrix multiplies.
Yeah, yeah, yeah.
But
And
what
then
you can do is you can shrink it a little bit, and then I guess what you get back is that this is a slightly more expressive thing than just
oh,
a simple up-down
gotcha.
dimensionality.
If you equivalent parameter count. Okay, and then the router on these one, that's just a learned parameter as well. Is that right?
Yeah, my understanding is that routers, nobody's putting effort into making them smart in the sense of which things should go to which experts because the experts are gonna
Learn whatever
understand
they get.
numbers or understand nouns or understand constitutional law better than other experts. Um, they're just pretty dumb.
So what is the loss function? I assume there's something that they take the model dimension in and they spit out um, kind of a softmax across the number of experts.
Yeah, and then
Um,
you do a top whatever.
okay. And then what's the loss function that's driving them? Is it just trying to get kind of equal energy spread across all the experts, or is it just
I think the
or it's
vanilla
random?
router has no explicit loss. It's just that if you always sent everything to expert 2, then you're losing expressive power by not taking advantage of all the other experts you have.
Oh,
And so you'll
okay.
get a slightly worse loss than if you spread everything out over a dozen different experts and they could each actually specialize.
So
So
it's
if I
just
may add
gradients.
to what Ted was saying, so there's a starvation related loss. So you don't starve set of MOEs and overwhelm only a set during
Yeah,
training time, and then that
right.
way,
I
yeah.
think that's the vanilla pressure that in order to get better eventual cross entropy perplexity, right? Now, separate from that, people have tried to do things, and DeepSeek worked really hard to additionally get the router to do very balanced mixing of experts. Okay, and that's a completely separate thing. That's not really about better performance. That's about I want my GPU utilization to look a certain way.
Yeah, it looks like I'd asked ChatGPT about papers related to MOE routers specifically. It looks like there's some work in the field as far as I can see. Like some, especially like some weird stuff, hash and static routing, router costs zero, stuff like that. Um, which, yeah, perhaps some further exploration warranted at some point.
Yeah. So, so at the end of the day, when we use mixture of experts, so the big thing is the most famous model before DeepSeek, V3 was Mixtral, and it had something like 8 experts. So it's a very small number, right? And then now you go to 256, and like this is a completely different phenomenon from right. So small number of experts versus large. So DeepSeek, I think, really broke the ice for large numbers of experts. And then what they did additionally beyond basic routing, Roger, is they said if you use 8 experts out of 256, then the way you maximize your GPU utilization is if you have at least 8 concurrent users, so that hopefully on average they're using different GPUs.
Hmm.
Okay. But what you don't want is you don't want each user to send data to one expert on one each of those GPUs.
Okay.
Because that's a lot of communication that then goes out and then has to come back and be combined. What you would rather is user one sent all of its stuff to experts on a single GPU A, and then the second user sent all their stuff to GPU B, and so on and so forth. That would be a lot less communication.
And
So they did actually add loss function penalties at one point to penalize you to sending it to lots of different experts, right? So they explicitly codified experts 0 through 7 are on the GPU A and 8 through 15 on B and so on. And so if you sent it to more than three GPUs, you would get penalized or something like that, right?
okay,
So,
so not
but that has nothing to do. Just so you know, so it is something they did, but it wasn't for LLM performance. It wasn't for language performance. It was for compute speed
or
performance by
communication.
reducing
Yeah.
the communication cost.
Yeah, yeah. Well, that's one of the ones I was wondering is that, and I'm not sure if they're doing this, but in more of a, let's say, like a mobile edge context, um, the idea of having these smaller experts, um, is it possible that if they were more domain constrained, could, I don't know if anybody's doing this, where you're bringing the expert weights in, like on demand out of CPU memory? It's different whether you're inferencing in the cloud where you're gonna have lots of GPUs, so you just have them all loaded up ahead of time. But I was thinking if I'm doing it on my phone or something like that, that having some of it in memory, some of it in GPU memory, and being able to swap in the experts as needed, it'd be the same type of thing where I don't want to spread it over all experts. I'd like a
Mm,
particular thread to be mapped to a few experts.
yeah, I don't want to say it's impossible, but certainly the path of least resistance is if you're running in the cloud on clusters with tens, hundreds, thousands of GPUs, you do MOE. And if you're running something on a single computer, laptop, device, then you use a dense model that does not use MOE.
Okay.
I was reminded there of the Gemma 3N paper. I was just hopped down to go check that one out, and but that's the I guess conceptually similar, like Matt Former thing, where rather than trying to have the ML the MOE router do that kind of delegation the way that they're doing it, that is sort of like treating them all sort of like little separate models, which I presume are trying to like run on the optimal number of threads on the like hardware constrained environment kind of thing. What I'm guessing.
Yeah, it's a little different because when they use the smaller stuff, they're not swapping back and forth. They're just simply saying use only the smaller one, and there's no like no parallel expert kind of thing. But yeah, it's a clever architecture. All right, we have another hand raised. We'll see if we can get through one model today. Yes, Jayant.
We could
Yeah,
do it.
the shared expert, what's the shared between what?
Yeah, you want to take that, Warren?
Shared. Let's see. I'm presuming that or like yeah, but if it's okay, yeah. So use of a shared expert. This is an expert that is always active for every token. So presumably, what they are sharing is attending to the token, and then I guess there's just like one that they put off to the side that's like, hey, always attend is kind of is the
Yeah, if you
impression.
scroll down a little, you can see the diagram. So in Mixtral, if you did like 2 of 8, then you would say, I want every expert to use exactly a quarter of the time if things are very evenly spread. Okay. But what they're doing with these 256 experts is they're saying, actually, this one, expert one is always getting used, and I'm doing 7 out of the remaining 255 spread evenly.
Hmm.
So your softmax doesn't even look at the first expert. It's just always used.
Hmm. Let's see.
And
So
and what's the motivation? Like what happens if you use or
Yeah, you
don't
can.
use a shared expert?
Yeah, Warren's got the paragraph right there.
absolutely, yeah. Well, yeah. So, unfortunately, I don't think it doesn't seem like
Okay.
a thorough answer, but they just said it boosts modeling performance compared to no shared experts, likely because common or repeated patterns don't have to be learned by multiple individual experts, which leaves them with more room for learning more specialized patterns, which makes sense to me. It's kind of like the sync token kind of thing, where if you have somebody to dump all the crap on, then the rest of the system can kind of do
Yeah.
the interesting stuff.
And again, if you're only doing 2 experts, you might want them pretty specialized. How much common knowledge is there? But once you have 8 experts, 10 experts, 12, 16 experts, you can imagine that there might be a certain amount of basic stuff that you just do with every token, regardless of whether it's a noun or a verb or it's whatever.
Yeah. Let's see. Summary. We made it. 671 billion parameter model that outperformed 405B llama, and it is much more efficient because of the MOE. And then the MLA instead of GQA was more between those collections of optimizations. It looks like it was quite a big deal for quite a while. Next up, we have Olmo, which is not a series that I hear about too often. But not the top of any benchmark or leaderboard. They are pretty clean and a great blueprint for developing LLMs thanks to their transparency. Let's see.
So if I can jump in, the key thing here is we've been talking about open source software for a long time, okay? And there's open weight models, which means you can download them and you know exactly what computation they're doing, but you have no idea how they were trained, okay? A truly open source model means that you have access to the training data set and you have access to the exact training code that they use to train the model. So that's where Olmo really stands out is AI said, hey, we're this is a truly open model. This is not just will let you use it for free.
Right.
So
Yeah.
it's reproducible work then.
Mhm. Exactly. And it's at least for the time, which is I probably at the time I guess it's kind of ancient history now, although maybe it's worth going back and digging into it. That if sitting right at the Pareto frontier of compute to performance, which is a good place to be, and then if you have the entire training pipeline to replicate from there, that sounds like a promising start point. But I'm sure we're, fairly past that by now, but I'll have to keep an eye out for future Olmos, I suppose. Let's see. Aim to focus only on the architecture details. What are the interesting choices? Normalization, placement of RMS norm layers, as well as the addition of QK norm, which I will discuss below. Still uses MHA instead of MLA or GQA. And largely follows the architecture of the original GPT. Switched from layer norm to RMS norm. RMS norm is old hat now. We will skip that discussion. I guess there's another article to follow up on. The placement of the RMS norm layer. The original transformer placed the two normalization layers in the transformer block after the attention module and the feed forward module, respectively. This is known as post-LN or post-norm. GPT and most other LLMs that came after placed the normalization layers before the attention and feed forward modules, which is known as pre-LN or pre-norm. A comparison is shown. Okay, sure. So we take layer norm, the op we're performing twice, and we're just kind of moving it around in our transformer block here.
Okay.
And then we have, let's see, pre-LN results in more well-behaved gradients at initialization. Furthermore, the researchers mentioned that pre-LN works well without careful learning rate warm-up, okay, which is otherwise a crucial tool for post-LN. Reason I'm mentioning that is that Olmo 2 adopted a form of post-LN, but with RMS norm instead of layer norm, okay. Instead of placing the layers before the attention and feed forward layers, they place them after, as shown in the figure above. Okay, sure, checks out. However, notice that in contrast to the original transformer architecture, the normalization layers are still inside the residual layers. Inside residual. Final layer masked. Let's see. Residual.
So if you look at the leftmost residual after layer norm, it is before the next layer norm, right? The residual, not
It's
the residual, the side part, the side part.
the side part.
Yeah. So
goes
this
through
one
the
here,
arms.
this is the residual. Versus over here, the residual is
Oh,
your RMS
Goes all
norm
the way.
inside that.
So it goes all
got
the way through.
yeah. Okay, cool. Let's see.
I-
The let's see. Why did they move the position of the contrast normal still inside the residual layers? Skip connections. Why did they move the position? It helped with training stability, as shown in the figure below. So pre-norm has all of these little spiky bits, and then post-norm has smoother gradients and better training stability. Okay, cool. Unfortunately, the figure shows the results of reorting together, which is a separate concept. Oh, okay, gotcha.
I have a question. Could somebody cover the RMS norm as opposed to layer norm?
I just looked that up before the meeting to refresh my memory because I was like, So RMS norm and layer norm all work on the model dimension, unlike batch norm, which works across samples. Okay. So so if your model dimension is 8,000, then basically you have 8,000 floating point numbers in the hidden representation for each token.
Right.
And what you're doing is you're normalizing across those 8,000 different floats for that one particular.
And so is that kind of keeping that on the hyper unit hypersphere then, forcing it onto the projecting onto the hypersphere?
So layer norm is more of the unit hypersphere, okay? And so the idea is you don't want your values to get too small or too big. You kind of keep them in this range between 0 and 1-ish, right? Which is where like all the action is happening with your activation functions. Okay. The main difference with RMS norm is it is not 0-centered, whereas layer norm is. So layer norm calculates a mean and subtracts it. RMS norm just does a scaling.
Oh, okay.
So it has these bias vectors that that you add after you normalize, and so basically, yeah, they're both keeping the sort of the magnitude in a manageable range, but layer norm explicitly says these manageable vectors have to be centered on 0, and RMS norm says, hey, you can center it wherever you want.
Interesting. Okay.
Mm. Uh, so did they just try out different, different positions and said, okay, this one is more stable, so let's use it? Or is there something more to?
You'll see in these other models, there's still not consensus. The most common form is pre-norm. This one is very unusual in doing post, and there's actually a model that's like, screw it, we'll do both pre and post. We'll cover all our bases. It's not that expensive. We'll just cover all our bases.
Right.
I see. Okay,
Hey,
thanks.
Warren, could you bring that GPT back
sure.
up real quick?
Yeah. Let's see. RMS norm slightly cheaper, has fewer learned parameters, and keeps the original signal's mean offset.
Okay.
Let's see. Training stability, sure. Typically
It-
very close.
But these are, Ted, these are both, they're not, they don't involve the batch. They're independent to each sample. Is that correct?
Yeah,
Okay.
that's correct.
Okay. All right.
So you're
Thank
mostly
you.
just dealing with exploding and vanishing floating point numbers.
Gotcha.
Hmm.
Okay. Thank you.
Now, just so you know, like you can still have spikes because, right, you have 8,000 dimensions. You could still have one of those 8,000 being huge, for example,
Yeah.
right? You're on average pulling them, but you're not forcing each and every individual float to be within a tight range.
Sure. Let's see. Oh yeah, I haven't been watching chat. I don't know if there's been people saying any.
You're
No.
good.
Yeah. Okay. Cool. Well, yeah. If there's anything we should pause and address in there, then feel free to. Or I have that put on my monitor now, so we should be good. Okay. Let's see. QK norm. Since previous section already mentioned it. Let's discuss what it is. Essentially, yet another RMS norm layer placed inside the multi-head attention module and then applied to the queries and keys before applying rope. Okay. To illustrate this, below is an excerpt of GQA layer I wrote for Quen 3, which is, okay. GQA is, we've got a module and we've got number of KV groups. Head dimension is none QK. QK norm is false, D type is none. If QK norm self, then we want an RMS norm over the head dimensions, or let's see.
So would this not matter in a MLA since it's kept separate, the positional encoding is kept separate?
So
In
this
the
is when, sorry, go ahead. Ed. Yeah.
no, you go ahead, Dave.
I was going to say this is when, so are they using MLA here or just MHA? Because that MLA was DeepSeek.
Right.
Let's see. So
Yeah,
QK.
right. This is not MLA, but Roger's asking like, what if? I don't. I'm not that familiar with QK norm. So basically, if you look at the forward function, Warren, you can see apply projections. That's where you take your input token X and you multiply it by the weight matrix to get your query or your key.
Mhm.
Okay. And then they have the optional normalization in the next big block after that. If having a large value in your query was bad, one of the things you could do is you could just decrease the values in your query weight matrix.
Okay.
So so it's a little surprising to me that you would get sort of outlier behavior when you multiply your X by the query matrix, because you can the query matrix could just lower its values. Now, obviously,
But
it doesn't.
yeah, I was going to say, but different. It would have different for different X's. It could have different gains, right?
So X as in like different measurements.
If the query, I'm trying to figure out how would you change the query to make sure that the query weight matrix, how would you change that to make sure your queries are the same as this
No,
normalization
I
observation?
just meant like during training, it could learn to have smaller values in that weight matrix if these are kind of too big. But
Yeah, I guess.
so this is not clear to me exactly what's happening here. So by that token, then I really can't answer what's the difference. I would imagine it's sort of the same with MLA. MLA is just a memory saving thing. It's not really intended to be that computationally different.
So this one is normalization versus MLA is latent mapping, right? So those two serve different purposes. Is your question that like if you combine the two, what will happen, or how does it
Well,
compare
I was
against
just
MLA?
noticing that it's applying it before applying rope. So I guess I was thinking that it was affecting the weight between the positional encoding and whatever the semantic portion of the query or key is, trying to keep those in balance. Which,
Right.
Yeah.
if you're doing MLA, you don't need to do that because they're kept separate. They're not added together.
Oh, I see what you're saying. I don't think this is about the competition between the semantic and the rope information. I think
Oh,
this is about taming to make sure you don't have outliers in your query and your key so that you get more stable dot products.
Right.
But I could be wrong because
ah,
I don't really know QK norm.
Right. And one thing, Pash, sorry, Ted, you go ahead if you had more thing to.
No, it's done.
Yeah. So one thing that I wanted to add is whatever this UK normalization is probably helping a lot because Quen models are more or less state of the art. In fact, for the last 6 to 9 months, any research work that is being done out there is using Quen models for publishing their research for fine tuning or any new things that they are uncovering. So, and if you look at the uh, results from different labs from Alibaba, so Quen is from Alibaba, they are amongst the best, if not the best, in many cases. So whatever it is doing, this probably is helping, amongst other things. I don't want to, say the other things don't help.
Yeah, it looks like this is it's like together with postnorm, it's stabilized. So yeah, it seems to me that this technique in particular is primarily for training stability, which presumably, it's easier to get a better model if your training is more stable. Is kind of is my deduction from that, I guess. Um,
All just as a side comment, all these normalization layers, it kind of sometimes is a head scratcher because we have these proofs about like what gradient descent will do, and then it's like, well, we just threw in 16 normalization layers. We threw this pre here and a post there and a QK there, and you've
right.
now kind of broken the rules, right? So
Yeah.
you say, oh, Adam does this or Muon does that, but it's like, yeah, except it doesn't exactly do that anymore because you threw in all these normalization layers that are bumping
Yeah.
things up and, you know,
Right. No, that's super well, and I feel like that's very interesting in that the I guess like relative resiliency of gradient descent, even if you just like chop off a bunch of numbers in the middle of it, is is interesting to say the least. I don't know, something about that algorithm, I guess.
Yeah, so
Um,
like an analogy might be if you had something mechanical, like I don't know, like a car and you wanted a nice smooth ride, right? If somebody was just like, just keep throwing more springs in there and that'll smooth things out.
right.
Like, but there can be unintended consequences if you just are randomly throwing springs in various places in your car.
Presumably, yeah. I
Yeah.
mean, it's yeah, might lose some stability eventually, but
Yeah. Oh, there could be like a harmonic oscillation somewhere.
yeah,
Whatever. I don't know, like
a thermodynamic car now, whereas
I'm just saying I'm exaggerating, but they are kind of just throwing these norm layers in willy-nilly.
yeah,
And
which is
do you think that the norm layers are they something fundamental, or are they kind of compensating for the numerical instability, of using a digital computer? Things are
So, so,
digitized, right?
so I definitely do not know, but that's my mental model is that they are just a floating point. Well, a combination of floating point compensation because you don't want overflow, underflow,
Right.
uh, but also we couldn't design a cleverer model where the activation function was working really well and we wound up with a lot of dead neurons. So we just threw a normalization layer in and now we have fewer dead neurons.
Oh.
But the behavior of the neurons has been changed. Whatever, we have fewer dead ones. It's probably good, you know.
well, I think you raise an interesting point there in that between so like we have like mixed precision weights and a bunch of normalization layers as is like how much in terms of having a gradient descent that still works, like how much can you get away with just replacing everything with just arbitrary normalization values is kind of an interesting thought, I guess. um,
Yeah, there's enough millions of dollars going in that people are trying stuff, and so
right.
they probably are chasing the signal for what works best. But I don't know that we know why anymore. It's just like somebody was saying, Quen, they've got big bucks. They've tried lots of different, and if they say, yeah, it's better with QK, they're probably right. But it's just I don't think anybody really knows why.
Right. Yeah, and that's well, yeah, I think that it's kind of a truism about the field in general, at least when it comes to these things. It's like this just continues to keep working. And it's very difficult to explain exactly why. Let's see. Noteworthy architecture design decisions are primarily placement of RMS norm, RMS norm after instead of before attention and feed forward, as well as the addition of RMS norm for the queries and keys inside the attention mechanism, i.e. QK norm, which both together help stabilize the training loss. So lots of stabilization shortcuts. Um, Relatively similar, except still uses MHA instead of GQA, although, okay, released a new variant. Very, very cool. Yeah, okay, so we've got Gemma 3 up next, which models have always been really good, underhyped, according to our friend Sebastian here. Rather large vocab size and the stronger focus on the 27B, true. 27B is a nice sweet spot. Um, Discussed earlier, use an MOE architecture to reduce memory requirements at inference given a fixed model size. Different trick, which is sliding window attention. Originally introduced in the Longformer paper and also already used by Gemma 2. Gemma 3 was able to reduce the memory requirements in the KV cache by a substantial amount, as shown in the figure below. Okay. Regular attention, sliding window attention, more memory efficient. Checks out to me. What is sliding window attention? If we think of regular self-attention as a global attention mechanism, since each sequence element can access every other sequence element, then we can think of sliding window attention as local attention, because here we restrict the context size around the current query position. This is illustrated in the figure below. Checks out. Cat sat on the cat sat on the is out. So we just have the cat sat. The current token can only attend previous token within certain limits. Gotcha.
Some of you have heard me gripe before, but if you look at this particular figure 12 here, for whatever reason, some lazy person who created one of the earlier versions of this query key thing did not label the axes to say which is the query, which is the key, and where's the beginning of the string and where's the end of the string, although you can kind of intuit from the cat sat on, right?
Right.
And somehow everybody took that as a cue that we can also be equally lazy and not label our axes. And this is a huge pet peeve of mine.
Fair point. Well, yeah, the relative accuracy of graphs in this industry is also another mystery to me because they seem to be wildly inaccurate all the time. Um, let's see. Let's see. Local attention because yep, global attention. Yep. Okay. Also used it before in Gemma 3 that they adjusted the ratio between global and local. Interesting. Gemma 2 is a hybrid attention mechanism that combines sliding in 1-to-1. Okay, each token can attend to a 4K token radius. Used as sliding window attention in every other layer. Gemma 3 now has a 5-to-1 ratio, meaning that there's only one full attention layer for every 5 sliding windows. Interesting. Moreover, the sliding window size was reduced from 4096 to just 1024. More
So
efficient.
they got a lot more aggressive.
Yeah, it looks like it.
Yeah. So when they first came out with sliding window, what people tried doing was replacing all of the attention with just sliding window. Because they're like, how often do you need to attend to anything more than 1,000 tokens ago anyway, right? And it turns out that, well, sometimes you really do.
Right.
So then, yeah, Gemma 2, they went 50% savings, and now they went 85% savings by having these small sliding window. And then what you hope is that since the model was trained with this, that if it really needs to recall some fact from long, long ago, then it has learned to use every 6th layer for that kind of functionality.
Interesting.
I had a couple of questions that Ted that came up in here. One is I assume that they do it layer wise rather than head wise because of computational like latencies.
Yeah, and it would just be
You,
really weird to have different dimensions on different heads. Like all the heads get calculated in parallel anyway.
yeah. Well, I could imagine like some heads learn to have long context while other ones have shorter. So kind of rather than have dedicated layers, you could have dedicated heads. Um, but I don't know. I haven't
Yeah.
thought through the math. Maybe there's a way you can make those all. You want all of them to finish at the same time, so you'd have to have something fancy then.
Yeah,
Um,
and we train these models with dropout, so we encourage a lot of distributed representations and redundancy.
yeah,
Um, so it so like it's very easy to believe that if there were a particular kind of functionality that happens in attention and you wanted it to be able to look way, way, way back, the model could learn to use layers 6, 12, 18, 24, you know.
yeah.
That for me is very easy to believe.
The other question I had here is, has anybody played with not a, so here we have a window, sliding window or global, but is there anything that would prevent you from having different sliding window sizes at different layers? So, you might have every fifth, maybe right now is a global, but you could have every third one be, window 4 times the size or something like that. Um,
Yeah. My guess is just from what Google did that they were kind of conservative in Gemma too. They're like, well, we'll save a little bit by doing um, every other, and then they realized they didn't need to. They could be quite aggressive. So if it works well at 1024, there's not much value in going below 1,000
Yeah, no,
because
I guess I
the
was thinking the other way, trying to avoid the
right.
global. Yeah.
Right. So if you need some global, then that's global. That's just going to be your context length that you're going to pay the full price.
Yeah.
But if you can get down to 1,000 and it works great, then you really probably at that point you stop. Even
Yeah,
if
I
you can
guess
get
you're
away
right.
with 512,
You've
it
saved
saves you.
80% already. Yeah.
Right, right. It's going to save you, 1 microsecond every 20 layers. It's not like,
Yeah.
buying you much.
Well, also memory size though too, right? It's not just the computation time, but the context window memory footprint.
Yeah,
But
there.
if you do it every fifth, then you've already saved 80% of your memory. So I can see
Yeah.
where it's diminishing returns.
Hmm. Yeah, it checks out to me.
May still be.
Let's see. Okay, so Sebastian wants to briefly go over the placement of normalization layers. Gemma 3 uses RMS norm in both a pre-norm and a post-norm setting around its group query attention model. Similar to Gemma 2, differs from the post-norm used in the original transformer, the pre-norm, which was popularized by GPT-2, and then the post-norm flavor in Olmo 2 that we saw earlier. Okay. Which we have, so this is our Olmo, which has the residual there. And then this has two blocks each for one. And we're doing rope and sliding window attention down here. Okay, so this rope's at the same location. What's the 32 and 34 here?
That's the number of layers.
Oh, okay, got it. Oh, okay, yeah. Checks out.
By the way, this will probably be our last model for today for time reasons. If you notice at the top, it has the vocabulary size.
Yeah.
And, I remember a time when we were talking about 30,000, 50,000. You look at these models, that they're all over 100,000. And so I think Google was going for a more multilingual model, which is one of the reasons why you see their vocabulary is one of the largest at 250,000.
Hmm.
These are very large vocabularies.
Yeah, especially for like a 4 billion model. I feel like that's like unusual for
Yep.
of that size.
Ted, I'm noticing as we're looking at this and the norms are all placed outside of the residual stream, which kind of feels intuitively right that you retain that residual stream clean all the way down through the model, through the layers. But I remember talking about the residual stream getting noisier, louder and louder as you went higher in the model. And there's not really anything that's pulling that back here, is there? Nothing that's pulling down the noise level as you go up.
No, it's a simple cheat. So if you believe in the linear representation hypothesis, then if the residual stream has the value that's pointing due east on it, if you want to switch that to due north, you have to sort of subtract out the east and write north, and it's a lot more work. But if you just write north really loudly at a volume 5 times greater than east was written, then you don't really have to do the subtraction. You just
Right.
so if you're sure enough of what you're saying, you just shout it really loud.
But and that makes sense. And that's kind of the definition of that getting louder as you go
Yeah,
up the layers, right?
yeah.
But louder is also, isn't it? It's worse from a numerical stability perspective. Um,
I don't think it's that much louder, right? So if we're just talking about a factor of like 20, like, yeah, it's floating point.
okay. I thought the whole problem with the noise was a noisy residual stream was that it was getting too loud and you were losing the ability to represent it within your float. But you're
There
saying no, you
are
don't.
issues, but I don't think this phenomenon is a particular problem.
Okay.
Yeah, if I remember correctly, it was interesting to me, it was either GPT-OS, OSS, or Kimi K2, or possibly both, that they did a really weird number of dimensions in the residual stream, being as we're on the topic. And I wonder if dimensionally, if you were to have, like, you might be able to compensate for an excessive amount of noise in the stream if you were just to like slap some extra dimensions for the noise to fit in on there, maybe. But that's like a kind of an out there, I guess, thought.
Yeah, model dimension is one of the most expensive things to grow.
Mm,
So that's, you're absolutely right. And that the reason why people don't just do that super quick as one of their first choices is because it's one of the most expensive. Assuming you leave other things sort of the way they are, you know.
right.
You're,
Yeah.
you're
Mm.
Why is that? What's the math that makes that one of the most expensive? Is it because it's a linear increase in the KB cache?
no, it's because every weight matrix you have pretty much is proportional to your model dimension.
Yeah. Okay.
So, right. So if you increase it by 10%, then all your query calculations are 10% bigger, all your key calculations are 10% bigger, all of your in projections for the MLP are 10% bigger, and all of your out projections for your MLP are 10% bigger. So you've
Okay.
basically just bigified everything in your model.
Okay. A kind of linear scaling of the model based on the width, the
Yeah.
model dimension.
Whereas
Okay.
other things you like, if you add the number of layers, well, you're only just adding a couple layers at the top
Gotcha.
instead of making every single thing.
That makes sense. Yeah. Yeah. But that more layers, so like, well, these are very close, but more layers increases latency though, right?
Uh, yes, but I don't think with modern serving that that's anything people really worry about.
Hmm.
I
Okay.
think what they're really just worried about is how much bang do I get if I increase from 36 to 40 layers? And if you get like a 0.1% increase, but by adding more parameters elsewhere, right? If you said I'll add more experts or whatever, and that gives you zero point 0.2, then you're better off doing that versus adding more layers. So for
Gotcha.
whatever reason, for like computer vision, ResNets, right? ResNet 151, you have this
Right.
model that's 151 layers deep, and you really don't see, more than whatever, a few dozen, 4 dozen, five, 3 dozen, 4 dozen, you know, such layers. You don't see 100, and so it does help from what I remember reading at smaller scales, but it doesn't seem to help a lot. It seems to plateau once you get past around 40, 50 layers.
Okay.
Interesting. Yeah, the in terms of like denoising the residual stream, it looks like GPT NeoX and Palm might be worth looking at. It looks like they have an explicit residual scaling coefficient at each add. So that's kind of our quote unquote RMS norm for
Those are
our
both,
yep.
I think, pretty old.
Yeah, pretty old, I think. Which I'm curious if like explicitly scaling. Well, yeah, I guess it's because the messing with this it since the residual stream changing the dimensionality is so expensive. If you don't have to do this and you can just like yell louder, then it makes sense to me that they could have like done this for a while and then been like, okay, we actually don't need to do this at all. Um, Interesting. Let's see. We've got Gemma 3. Okay, so there's our relatively intuitive approach. Best of both worlds. In my opinion, a bit of extra normalization can't hurt. Interesting. More springs does not make the car worse, according to Sebastian, at least. In the worst case, if the extra normalization is redundant, this adds a bit of inefficiency through redundancy. In practice, since it's relatively cheap, this shouldn't have any noticeable impact. Well-performing open-weight LLM, bit underappreciated. Most interesting part is sliding window attention to improve efficiency. Interesting to combine with MOE in the future. and then unique normalization layer placement with RMS norm layers before and after the attention and feed forward modules. And then we get a quick bonus on Gemma 3N.
Do we
Would
quick time check? We're at 8:02. Do we want to leave this as a starting point?
Maybe we'll leave 3N for next session.
Yeah, it sounds good to me. It's either we wrap up the gemmas or we can kick off with the gemmas on the next episode, as it were. Sounds good.
This one is I'd like to start with it because I'd like to understand this PLE a little more.
Sure.
Okay.
Definitely.
And so just a quick comment to wrap up Gemma. Gemma is not really a frontier model. Okay. So when we're comparing these architectures, there's some choices like when I think Dave was talking about Quen, where they're just saying this choice will give me the absolute best language modeling, right? You'll notice this, we're talking about a Gemma 3 4 billion model. This is now, what will shrink my model to make it less memory, less compute with the least harm to it? So I don't think you'll ever see sliding window in a frontier model. You're not going to see Quen 4 use sliding windows.
What do you mean by frontier model then? Are you
So I'm talking about your
the big?
your GPT-5s, your whatevers that are just going for the state of the art, the best reasoning, the best coding, the best benchmark performance, versus here's a model that might run a laptop. Here's a model that we might fit on a phone. Here's a model that, maybe it doesn't quite fit on a single computer, but it's something a business could, fine tune without tens, thousands, hundreds of thousands, millions of dollars,
Warren, can you scroll back to that? What was it called? Pareto Frontier?
Yeah, yeah.
That was for Olmo, I think. Yeah.
Mm-hmm. Yeah, and I just threw it at GPT to look into it. If there's anything that's topping leaderboards that does use sliding window attention, I feel like there was something, either GPT OSS or Kimi, or I don't know. Those are just on my brain lately, I guess.
I don't think so. Yeah.
So Ted, when you talk about this, if you define the frontier as this edge here, those are all interesting for different.
Sorry,
hardware.
frontier model and Pareto frontier are two different concepts.
Yeah. Okay.
So frontier model is just the top 5%
Yeah,
of whatever the current line is.
Right.
Yeah, I think by frontier we mean like for this model we want to squeeze every bit of performance that we can get out of it because we want to top the leaderboards. Whereas with Gemma, it's sort of the inverse problem of like, okay, how much can we squeeze this model down without making it useless, effectively?
Yeah. So on this graph, you really only see Quen 2.5 14B. That's not even really way up there.
Although interestingly, it looks like GPT OSS does use sliding window attention on every other layer.
I don't call that a frontier model.
Fair point. But interesting nonetheless. I think that because I remember, or at least because I remember I sort of ran with it, Ted, when you were like, it seems silly to do a MOE kind of that size if I'm supposed to run it on my own machine. But I was kind of finding that, at least among the other people that I know that were like trying to run things locally, basically where people were at was like, we just don't use dense models anymore, just because the various sort of like tricks to play with MOEs are just so much more efficient that there's kind of no reason not to. Has been my general finding.
I don't know. I don't think you can swap experts like Roger was talking at some point about swapping. I don't think you can swap experts fast enough. So then with MOE, you just need a lot of GPU RAM.
Yeah, I think it was it was Quen, I think, last couple of days. They did a really weird MOE arc. I'll have to take a look at it, figure out what I'm talking about.
So Ted, when the MOE's in the cloud and shared users, you have to have all the experts loaded, right? but there's an advantage for each user only requiring some subset of those GPUs for its particular inference.
Correct.
So it's not
Correct.
about the thing I was talking about between CPU memory and GPU memory, but it's just how much of the GPU memory do I need for my one request in this big batch?
Yeah, exactly. So for big cloud models, absolutely use
Yeah,
MOE. And let's say you've got 20 times as many experts as you have any one user using, then you basically have 20 GPUs. But if you have 40 users on the system, you're hoping that two of them are allocated to each GPU and it kind of averages out.
right, right.
But if you are the only user on your computer, then you have to have all 20 of those loaded, and
Yeah,
you're only using one at any one point in time.
then it hasn't helped you much. Yeah.
Right. So
Unless you could get the context that I was talking about.
yeah, unless you could somehow swap them in and out really fast, which
Right.
I don't think
Hmm.
It
you
probably
can.
doesn't work. Yeah.
Um, so there may be some really great small MOE models, and who knows, maybe at some point we'll find, but it seems like it's a not GPU RAM conserving maneuver. So,
Well, yeah, what I was saying is you have to start somewhere. So I would pick just doing temperature and top P studies on some quantitative data, get your results, publish it, and then move up. It's going to be hard to start on an LLM, from what it sounds like. So, with anything, you have to start small, publish, and it's just that same thing. You have to iterate, and everything has to get better over time. But to be part of the field, it's going to be really hard to get a job right away in industry because these are already the experts. So you're probably going to have to show your potential employer that you've been, actually doing the results, and it's something you could share.
all right.
Indeed. Yeah, that's I suppose we can call that a wrap for the week. And then yeah, let's see. Yeah, I'll have to see if I can chase that. I don't because I remember what like when you were saying that it made a lot of sense to me, but for some like when I was sort of like shopping that around a little bit, I didn't get like a um or rather a lot of people really liked the architecture of GPT-OSS, which was a like the main thing that stuck out to me about the architecture was that like they're like, oh yeah, you can run this on your local thing, but it's like a giant MOE for no reason. But it didn't seem like anybody else really cared about that. So I wasn't I'm not sure if there's like something I'm missing, or if it's just like we don't really care about maximizing the usage of our GPU memory anymore. It's just interesting, I guess.
I did
Yeah,
a
I
quick
mean,
search on
I'm
Grok,
gonna,
and it's not within reason. I mean, you can't, pre-train any of these, let alone I think fine tuning is outside of the reach, even if you have hundreds of gig of RAM. So you're just looking at like, obviously if you want to use proprietary data, but to do other studies, there has to be other studies that people are doing that are efficient, prove a point, help affect the field in a positive ways, but it doesn't take like over $10,000 in compute.
Oh yeah, I mean anything I want to do, I'm going to do on Nano GPT first, but after
yeah, I think
that,
that was Ted's comment is that was kind of the route they were
yeah, and
going.
maybe there is a performance trade-off here because I'm looking at like, your 20 billion model, you quantize that, you can fit that on a single GPU and and maybe you get a better performance profile with like it being, active 3, 4, 5 billion instead of
yeah,
instead
that's
of
I'm wondering if
dense.
that's the thing or not, kind of. I might need to
Um,
explore
I think
more.
but
it's really good to have a backup, if any of these proprietary models, if the internet goes out or anything, for your core operations, I'm sure already people have implemented their own custom, models locally.
Well, yeah, I mean, at least for me, like in terms of the question that I'm trying to answer is like, regardless of how many people I'm serving, end of the day, in terms of like the farthest I could in theory push a model, is there like let's say I have perfectly optimized every component of the model that I could possibly optimize. At the end of the end of that optimization, do I end up with a sparse model or a dense model? Is kind of the question that I'm thinking about, essentially. If
Everything just compresses down like Llama. Everything's like, I couldn't even run 48 gigs of RAM compressed Llama 3 70B. It wouldn't even run properly. And that's just inferencing on it. So it's, the requirements are high. But that I still haven't given up on the idea that if you could take just a piece of the LLM and test it appropriately with other pieces of the main LLMs and then make an impact on that on minimal hardware. Obviously, you can't do everything because you don't have the rest of the LLM, but
Well, I think that's explicitly what they do in 3N, right? Is they kind of they chop it into parts and then try and fit it on something small, if I'm not mistaken.
yeah, just to find some type of test, like unit tests, like does this specific component work any better than whatever, and then, you know, get better at it.
Okay, I'm going to go ahead and stop the recording, I think.
Okay.
Then we'll continue, pick up Gemma 3N next week.
Yeah, that seems good to me. I will put it on my calendar louder, hopefully, and then I will